In just a few years, artificial intelligence has burst into our lives like a meteorite. And since then, almost everyone has been watching with as much fascination as fear the most visible effects it produces, namely, these oceans of texts, images, and videos generated on demand. But this spectacle is only just the tip of the iceberg. Long before the general public started having fun creating astronaut cat videos or asking questions to large language models, artificial intelligence had already quietly entered laboratories. There, thanks to its ability to detect faint signals in the piles of accumulated data, it has shaken up entire fields of research, sometimes enabling truly mind-blowing breakthroughs. I want to tell you about this ongoing revolution today. Since the subject is far too vast to fit into a single video, we'll focus here almost exclusively on the brighter side of the story. That is, on the discoveries and accelerations that suggest progress, with overall positive repercussions. And next week, we'll take a look at the flip side, focusing on the excesses and scenarios where the emergence of this new power could turn dreams of a bright future into nightmares. The first field of research where artificial intelligence has vastly expanded what's possible is structural biology, which studies spatial organization of the macromolecules that make up living beings, and more specifically proteins, those key molecules responsible for how our cells function. To understand the magnitude of the upheaval, we need to remember that over the past decades, long before the advent of artificial intelligence, research teams had already managed to identify the possible chemical formulas of nearly 200 million proteins. But their arrangement, their three-dimensional structure, which determines what they can or cannot do, remained extremely difficult to determine. To grasp the extent of this difficulty, we need to remember that an average-sized protein contains between 300 and 500 amino acids, and that each amino acid, in a way, adds something. Degrees of freedom and additional constraints that allow the whole to fold in a unique way. Thus, being able to predict the three-dimensional shape of a protein could require months of research. Before 2022, despite the efforts of laboratories, out of the millions of known proteins, the spatial configuration of only a few tens of thousands of them was discovered each year. And then, AlphaFold arrived, and in just over a year, this AI system, developed by Google DeepMind, managed to predict the structures of 360,000 new proteins from the amino acid sequences that make them up. A number greater than all the forms that had been discovered since the existence of structural biology. And in 2022, the improved version of AlphaFold managed to predict the three-dimensional shapes of the 200 million proteins present in our databases. A sensational discovery that earned the researchers who developed this artificial intelligence model the Nobel Prize in Chemistry in 2024. Today, AlphaFold 3, like other models developed in generative chemistry, is even starting to tackle the prediction of potential affinities between molecules by trying to predict their toxicity, their stability, and their ability to bind to a specific protein, sometimes with remarkable results. In a Le Monde article published this year, Alexandra Carbon, a researcher specializing in modeling interactions between molecules, explains that by feeding and training artificial intelligence models, using databases accumulated over decades of previous research, which contain millions of calculations of forces between atoms, researchers are now able to evaluate the interaction between two molecules that seem interesting to them in just one night of calculations. Whereas before the advent of these new tools, it used to take nearly 4 months of effort. Being able to identify a potential therapeutic molecule much more quickly through simulation does not in any way allow us to bypass all the lengthy but necessary steps required for drug development. But AI already makes it possible to avoid following the wrong leads from the start. Another field of research in which artificial intelligence has made a dramatic breakthrough is neuroscience, where it has enabled the creation of the very first complete brain maps. Now, let's return to our story. The video you are currently seeing on the screen shows you the complete map of the neural connections in the brain of an adult fly. You can see the roughly 139,000 neurons and more than 50 million synaptic connections, making up the connectome of this insect, which the Flywire project has made it possible to fully map. Creating a complete representation of the neural connections running through a brain, even one as small as that of a fly, is an absolutely mind-boggling task that, until recently, was out of reach. But the artificial intelligence algorithms developed by the Flywire team made it possible to study thousands of ultra-thin slices of a fly's brain. They imaged them with electron microscopy, then virtually reconstructed the neural extensions from these images, and in this way created the first complete map of a complex brain. We are still very far from being able to tackle volumes comparable to those of the human brain, which, with its tens of billions of neurons, remains for now an unreachable peak. But projects like this are base camps for venturing further, especially since the study of larger connectomes has already begun. The Microns project, also fueled by artificial intelligence, has made it possible to map, down to the individual cell, 1 cubic millimeter of the visual cortex of a mouse brain, in which about 75,000 neurons, 200,000 cells, and 500 million synapses have been digitized. In the future, these maps could help us better understand our brain, and maybe even find solutions to disorders related to how it works. Without needing to rely on these detailed maps, over the past 2 years, teams of researchers have managed to develop neural prostheses incorporating AI and capable of translating into words the neural activity in the cortex associated with speech, at a speed of 78 words per minute, whereas previous assisted communication systems struggled to exceed just a few words per minute. Knowing that the pace of natural speech is around 150 to 180 words per minute, these innovations are beginning to allow people who have lost the ability to speak, such as those paralyzed after a stroke, for example, to communicate. In microbiological chemistry as well, artificial intelligence has enabled major advances by greatly expanding the range of possibilities to explore on paper. Keep in mind that before the advent of AI, we had only identified about 150,000 inorganic materials, of which only 28,000 were considered stable and technologically interesting. And then, in 2023, GNOME from Google DeepMind arrived, and in just a few months, it discovered nearly 2.2 million new crystal structures, of which about 380,000 are theoretically stable materials. Thus, multiplying by nearly 13 the number of potential candidates to improve the efficiency of batteries or solar panels, as well as to develop more efficient semiconductors or catalysts. You have to understand that materials chemistry is an absolutely gigantic space of possibilities, because depending on the synthesis methods, the temperature, the pressure, and the proportions of the elements involved, and the way they are combined, it is possible to end up with materials that have extremely different properties. In this dizzying space of possibilities, researchers have long made progress by groping around, like explorers whose headlamps only illuminate part of the underground tunnels they are visiting. And then, artificial intelligence came along and made it possible to considerably widen their beam by suggesting ingredients and recipes that had remained hidden in the shadows. Here, just like with therapeutic molecules, knowing that a material can potentially exist does not completely solve the problem. Then you have to find an effective way to manufacture it, and then check that its expected properties actually match the predictions. But the time saved by not wandering through the dizzying maze of possibilities, paths that lead nowhere or end up in dead ends, is more than significant. A concrete example among many others. In 2024, a model developed by Microsoft screened the 32 million potentially interesting crystals we know of for building solid-state batteries. After 3.5 days of calculations spent eliminating unstable structures and chemical dead ends, the model managed to identify, in this ocean of combinations where a human would have drowned for centuries, 18 promising candidates. Examples of this kind are legion in all advanced industrial sectors where materials, structures, or shapes with very specific properties need to be developed. In these fields, artificial intelligence can serve as a giant digital funnel. It shakes up millions of possibilities, eliminates mediocre solutions, and helps to identify the few most interesting options more quickly. To accomplish these feats, the models are fed with carefully accumulated experimental data and with simulations carried out on supercomputers. Then, from this raw material, artificial intelligence searches for hidden patterns and learns to produce surrogate models, that is, quick approximations of phenomena that classical numerical methods take much longer to compute. In some cases, these surrogate models can provide a useful approximation 100 to 1,000 times faster than classical numerical methods. Thus, in many laboratories, AI is becoming a kind of high-speed digital wind tunnel, which allows, in fields as varied as fluid mechanics, aerodynamics, acoustics, or even mechanical engineering, to test more shapes and materials more quickly, before moving on to more computationally intensive numerical simulations or real-world experiments. However, it should be noted that this impressive ability to perform accelerated natural selection still shows serious limitations as soon as the models are made to work in new physical regimes or in areas poorly represented in their training data. As shown by the ongoing revolution in the field of weather and climate sciences. Between February 2022 and January 2023, several global weather forecasting models, developed by NVIDIA, Huawei, Microsoft, and Google, and fed with collected weather data, using weather data collected since the 1940s, have proven capable of making forecasts that are roughly equivalent to those produced by major traditional numerical models, while requiring 1,000 to 10,000 times less computing power, with 1 minute of simulation running on the AI model on a computer equipped with a good graphics card. This way, we can achieve results comparable to simulations that run for 2 to 3 hours on supercomputers. Except that these artificial intelligence models still struggle to accurately predict the occurrence and evolution of extreme events, such as storms or heat and cold waves. So traditional physical models that simulate atmospheric dynamics remain absolutely essential to climate science. To shake up the officiel commence également à bousculer the most abstract of all sciences, mathematics. A field of research where just a few years ago, no one expected it at all. And then, in 2024, a first step was taken, when the AlphaProof and AlphaGeometry models, both from Google DeepMind, managed to solve 4 out of the 6 problems presented to participants at the International Mathematical Olympiad, thus earning the equivalent of a silver medal. This result surprised more than a few people, because to be able to solve the problems presented at this high-level competition, intended for students finishing high school, you don't just need to know how to calculate, you have to be able to line up arguments and build rigorous chains of logical reasoning. The following year, other models faced with the problems from this competition managed to solve 5 out of 6, thus reaching the threshold for a gold medal. And then, artificial intelligence kept progressing. And in January 2026, GPT 5.2 Pro, which is the paid version available to the general public, independently solved an Erdos problem. The kind of problem that some of the best mathematicians had been struggling with for decades. In recent months, many similar problems have been solved. Often, the solutions found by artificial intelligence turn out to be rediscoveries of results already present in the scientific literature, and the authors who were working on other projects didn't realize they had come close to the solution. And then, at the beginning of May this year, the mathematics community was stunned when GPT 5.4 found a construction that refuted it. A major conjecture, meaning a statement for which we don't yet have a proof, but which we believe to be true. A conjecture that had resisted proof since 1966, and that GPT 5.4 solved by taking lines of reasoning that no one had used to tackle this problem until then. If you want to dive into the details of this absolutely mind-boggling breakthrough, I recommend the very well-documented video that Mr. Phi made on the subject. A week after this breakthrough, Timothy Gower, Fields medalist in 1998 and professor at the Collège de France, announced on his X account that he had solved open mathematical problems whose proofs could make up a thesis chapter in just a few hours using GPT 5.5. AI is also starting to spark a small revolution in formalization processes. These consist of translating mathematical proofs into formal computer language, so that software can check line by line that each step of the reasoning is sound. In February of this year, the proof that earned Ukrainian mathematician Marina Vyazovska her Fields Medal in 2022 was formalized with the help of an AI created specifically for this kind of task. This work of producing logical code, which would have required months of effort from researchers not long ago, was completed in just a few days by AI. We are still far from the automatic formalization of all mathematics, but we are beginning to see AIs that help seal proofs in the cold marble of formal logic. These models could eventually help certify already published complex results, as well as to explore theorem libraries more quickly, thus freeing researchers from some of the logical bricklaying so they can devote themselves more to the architecture of their ideas. Finally, in observational sciences, the ability of artificial intelligence to search for patterns in vast amounts of data saves a significant amount of time, and to accomplish tasks that, just a few years ago, would have required the intervention of supercomputers working for entire days to complete. In the field of numerical cosmology, which simulates accelerated universes to better understand the effects of dark matter, dark energy, or even the distribution of galaxies at large scales, the arrival of artificial intelligence has made it possible to emulate many more versions of the cosmos. Recent studies have indeed shown that deep learning methods can turn low-resolution simulations into super-resolved ones. And above all, that AI could generate, in 16 hours of computation on a single GPU, a virtual universe as vast as those that require months of calculation to be created on a dedicated supercomputer. And progress doesn't stop there. In the field of nuclear fusion, artificial intelligence models now make it possible to optimize confinement parameters and better predict the onset of plasma instability. In particle physics, they improve the efficiency and speed of processing the avalanches of data produced by large accelerators. Finally, in astronomy, the use of AI makes it possible to scan the staggering amounts of data collected by modern telescopes to detect faint signals buried in noise, thus facilitating the discovery of new objects. ExoMiner, the deep learning model developed by NASA, is trained on planetary transit signals and has helped validate the discovery of 370 new exoplanets in the data collected by the Kepler satellite. In 2021, a research method using machine learning has also delved into the data accumulated by the DESI instruments, which focus on the distribution of distant galaxies, and it made it possible to detect 1,200 new gravitational lenses, thus almost doubling the number of these phenomena known at the time. More recently, an analysis method incorporating artificial intelligence and designed to analyze the nearly 100 million images taken by the Space Telescope, Hubble, managed in just 3 days to identify more than 1,300 distant objects that had previously gone unnoticed. Meanwhile, the Hubble Asteroid Hunter project made it possible to discover more than 1,000 new asteroids in the telescope's archives. In short, wherever there are complex images to interpret, AI is starting to make its presence felt. In the field of medical imaging, its deployment seems promising for increasing early disease detection rates by assisting doctors in interpreting tiny shadows drowned in a sea of gray pixels that need to be detected in radiology, mammography, and in MRI images. This ability to process massive amounts of data to uncover patterns also benefits fields such as agronomy, where millions of satellite photos are combined with weather data, information about soil types, and yield history. Artificial intelligence models can help better predict crop development based on climate variations, estimate harvests, and guide more rational water management. Recent work, for example, has succeeded in creating a global map of agricultural plots by processing images captured by the Sentinel satellite network. You might think that such maps have existed for a long time. However, they are extremely recent. The main difficulty lies in interpreting satellite images, since agricultural plots take on different shapes depending on the region and the unique history of each country. So, before the existence of artificial intelligence tools trained to recognize the boundaries of fields, we were often limited to detecting their borders through demarcation lines. Whereas today, the latest methods are able to take into account textures, colors, and how they change throughout the year to produce the kind of result you see on the screen right now. In epidemiology, the same principle is beginning to transform the way we monitor threats. Because AI models are now helping to analyze viral genetic sequences to detect possible mutations, estimate the potential of certain variants, and even improve spread models to identify the most exposed areas. In biodiversity monitoring, AI also allows us to change scale. Take birds, for example. Thanks to the huge amount of data collected by the global community of amateur ornithologists who participate in the eBird project, statistical and machine learning models can now produce extremely detailed maps of distribution and population trends. This makes it possible to see in much greater detail the major migrations, the declining areas, and the refuge zones, and thus to better target conservation efforts. In the same way, the deep learning model BirdNet, trained to recognize the acoustic signatures of birds, can now identify more than 6,000 species in complex soundscapes, and thus turn months of recordings into usable ecological data. In the future, deploying this type of tool could allow us to know the state of bird populations almost continuously. Even unlikely fields, such as archaeology, are also being affected, albeit only marginally, by AI, which has notably made it possible to read fragments of scrolls carbonized by the eruption of Vesuvius, thanks to models capable of distinguishing carbonized ink from burnt papyrus. Finally, there is a field of research that we don't necessarily think about, namely meta-science, which is the science of science. Today, even in cutting-edge fields, research produces more articles than a human being could ever read in an entire lifetime. Tools like OpenAlex automate the extraction of information from articles and classify, connect, and index nearly 500 million scientific publications. Are navigation tools that allow researchers to move more easily through this ocean of accumulated knowledge. By quickly identifying work related to different fields of study, OpenAlex also makes it easier to connect disciplines. Thus, a promising image analysis method developed in astronomy can be brought to the attention of teams working on similar problems, but in the field of medical imaging. In the gigantic scientific databases, we are also starting to see artificial intelligence models that can search through the literature to try to find forgotten connections. A system named Robin, which has explored a part of this ocean of knowledge, with the aim of checking whether molecules effective against certain diseases might also be effective for others. It was able to show that a drug developed for something completely different would probably act against chronic age-related eye degeneration. A hypothesis confirmed in the laboratory. A few months later, co-scientist, another artificial intelligence agent, helped identify therapeutic candidates against the disease. Acute leukemia, some of which were validated in vitro. In short, even though AI had already started to shake up scientific research long before it became a public topic, with the rise of deep learning and LLMs, the interface between human intelligence and the vastness of reality has increased considerably. In many fields, its ability to spot promising locks and especially to quickly try out keys to pick them already makes it possible to eliminate dead ends and explore paths that no one would have had time to take without it. But keep in mind that we've only looked at the glossy, almost idyllic side of this story here. Yet, many of its advances come with potentially much darker consequences. Because while the power of these tools allows us to shed light on new knowledge, it can also reveal things we might have preferred to leave in the dark. So join us next week to explore the other side of the coin.